Good afternoon, everyone. It's really my pleasure to be here. So thanks organizers for having me here. And I'm going to talk about the explosive transients resulting into supernovae and trying to convince you that we should spend some part of ngVLA SKA time in studying these objects. These are the 4 science cases I'm going to talk about. And the first one, if you find it very mundane, allow me 4 minutes of your time to convince you otherwise. So I want to say that with the surge of optical robotic telescopes, we are discovering thousands of supernovae every year, and less than 1% of the supernovae are seen in radio, or at least observed in radio band, and only 1/3 of them are being detected. But at the same time, one of the biggest problem in stellar evolution is connecting supernovae, different kind of supernovae, to their progenitors. We certainly do see some supernovae progenitors in archival images, but they are just showing the dying moments of the star. They're not telling you about anything about progenitor, because due to the extreme mass loss in massive stars, the progenitors of the star of these supernovae and the final, there is basically no mapping between the initial and the final mass of the star. And even if you try to understand the mass loss rate, it is very complex, affected by many parameters. So if you see just the y-axis of this plot where I'm showing the final mass to the 0-age main sequence mass, there are at least 50% uncertainties. So theorists are waiting for us, for our observations, to give them inputs in the mass loss rates, and it's upon us to understand them better. And thankfully, this curve of mass loss rate can become boon in radio band, because these mass loss rate will form the winds around the supernovae, and the ejecta interacting with this will give rise to radio emission. And not only that, because there is a difference of around 1,000 between the wind speed and the ejecta speed, depending upon how far you can probe toward the sensitivity limit, you can go back in the progenitor history and understand the progenitor evolution. And while we have data only in handful of cases, and we know it has always shown us some surprises. For example, this is a very famous case of supernova 2014C. When it was probed for a few years, it's showing a very standard synchrotron light curve, but when it was probed further, it showed another bump in the light curve, and that bump was explained as the ejecta running into this very dense shell, probably due to the binarity. Similarly, this another supernova 2001 EM, if you focus on this lower part, it is the GMRT spectrum, and it is following the synchrotron emission in optically thin part. And when we took the VLA data on that, we see this another component rising up, and this was actually seen in another supernova 1986J when it was 30 years old. And the VLBA observation in this case had very clearly shown this second blob of CSM, which is produced probably due to the binarity in a common envelope scenario where two massive stars, one of the compact remnant of that star is stripping the mass from the star and creating this very asymmetric kind of CSM. We have also seen this kind of signature in ALMA data, where I'm showing you a very latest example, 2018 IVC, where we saw this rebrightening. All of these cases have been linked to binarity in the supernovae progenitors. But the problem is that it is just a time stamp. It is not telling us anything about the overall binary progenitor scenario. It is not telling about how far these stars are in the binary system and how they're stripping the mass, what are their properties, at what stage they are starting to interact and starting to strip the mass of the star. So all of these things need to be found out, and for that, we really need the observations. We need to probe the sensitivity limit, and we need observations from millimeter band to low frequencies, because this is the nature of synchrotron as it peaks at lower and lower frequency at later time. So this kind of science is even more important in interacting supernovae. And these are the supernovae where the mass loss rate is so much that they're losing up to 1 solar mass per year. And in such a case, they're literally hiding the progenitor inside their dense medium, and there has been some studies, and there are multiple channels. In fact, there are some imposters which can produce these kind of supernovae, And as you can see on the right side plot, because the density is so high, they're all absorbed. It is very difficult to observe them at earlier time. Even when you observe, you don't detect them because they're all synchrotron self-absorbed or free absorption is happening. So in such a case, there have been some studies. Yes, there have been some studies that if you do some simulations, that even when we cannot observe at, say, VLA bands, if you do it at ALMA bands or hundreds of 80, 100 gigahertz band, you can do it at, you can detect these kind of supernovae. So here the blue one is the 100 gigahertz simulated light curve, and the purple one is the real light curve for a supernova, an interacting supernova. So I hope I have convinced you that to understand the progenitor history of supernovae, to connect the progenitor to the different kinds of supernovae, it is very important to have the observation, wide bandwidth coverage, and order of magnitude improvement in sensitivity. And I'm talking of sensitivity because no TAC committee gives so much of time to keep observing a supernova for a very long time, So you can do maybe supernova in 1 hour, you can detect something, but no TAC is going to give you like hundreds of hours of time to do 100 supernova, and then you need to do follow-up also. So if you have a much more sensitive system, you need less of the telescope time to do your science. This second science case, I'm going to talk about the realistic radio emission in homogeneities. And again, I'm going back to the synchrotron, where we're assuming that the electrons are accelerated in the magnetic field, and we assume the single homogeneous distribution of magnetic field, and we probe our synchrotron models. We forget the fact that the magnetic fields are enhanced in the nonlinear way on the Rayleigh-Taylor instabilities at the shock front. So we don't care about it, but data do. And so there have been many examples. When you see the supernovae, you see this deviation from the standard synchrotron model. And sometimes these are artificially fit with some artificial parameters, a broadening parameter. But whenever we have data, wideband data, we see that these kind of models do not comply with physically viable models. For example, this supernova, where we have the GMRT data in the optically thick band and the VLA data in the optically thin band, it shows the electron acceleration to be so efficient that we have not seen this kind of efficient acceleration in the universe. It's not physically viable. Or if you look at the data and estimate the size of the fastest ejector which radio is probing turns out to be smaller than the ones which optical information has given. So it means that these kind of models are failing, and we need to get more realistic models. So we have created a model where we are saying that the radio emission is superposition of the optical depth due to the range of magnetic fields, and that is causing the broadening in the spectrum. And this has certain implications. The biggest implication is that when we talk about supernova, we talk about some kind of supernova which have, central engine, or we talk about fast blue optical transients which have some central engine working. But if you don't get your velocities right because of the inhomogeneities, you are not able to talk about these kind of physics. So for that reason, it is very important to create these models. Unfortunately, homogeneities can also hide in various degenerate parameters, and for that reason, we need to have the optically thick and optically thin part of the spectrum, and even better, we need to have multi-epoch early time VLBI with LBA, ngVLA LBA, and late time SKA VLBI to probe these things. The third topic I want to talk about, which was covered a little bit in the previous talks, were energy budget in supernova. And again, we are going to this very simple spherical curve model where we assume that there is synchrotron is a game between relativistic electrons and magnetic field. And we need to assign the energy budget to them, and the easiest is to assign equal energy to relativistic electrons and magnetic field. But then supernovae are very dynamic system, and it is not possible to have equipartition all the time. So here I'm showing you a very famous supernova, 1993J, around day 3000. Left is the GMRT data and the right is the VLA data. And if you have just these two telescopes and you fit your model, you may fit some kind of synchrotron model, but when you bring them together, Yes, and you bring them together, you see that there is a synchrotron cooling. And since you know the age of this supernovae, one can actually estimate the magnetic field, and it turns out that the energy in the magnetic energy density is 10,000 times more than the one in the relativistic electrons. So in this case, in fact, we have combined the GMRT data with VLA data for many epochs, and we have not only seen how much energy is there in magnetic field, we have seen the evolution of magnetic energy distribution. So this kind of science is possible only in the wideband data. Unfortunately, not every supernova will show you synchrotron cooling, so you may not be able to do this kind of physics. And in that case, what comes to rescue is ngVLA LBA observations and SKVLBI observations, where you can actually measure the real size of your fastest ejector, your supernova. And from the radio modeling under equipartition, you estimate the size and you compare the two sizes, and that will tell you how much energy, disbalance is there and how much energy is distributed in what kind of system. Again, some of these things have been done, but in very nearby cases, and just one or two examples are there. So I want to probe that accurate energy budget. We need wideband SKA and ngVLA snapshot observations of a few epochs. And we also need the VLBI observations, so that we really need to get into the accurate energy budget. And the last science case I want to talk about, since we're talking about the energy, I want to go back to interacting supernovae, and I want to tell you that when the density is so high, there are chances that there are inelastic proton-proton collisions, which will give rise to pions, and these pions decay will give rise to secondary electrons. And it is possible that these secondary electrons will also give rise to synchrotron emission. Of course, none of these things have been seen yet, but it is a high risk, high reward kind of science. And if one sees these kind of things, it is going to probably solve one of the big mysteries of cosmic rays beyond the Ni3 PeV, which is supposed to come from extragalactic, but we don't really know where they are coming from, and supernovae may be contributing towards that. So the idea is that these simulations have been done, and if the density is high enough, it has been seen that the early emission, the early emission will be, what's happening? Okay, the early emission will be dominated. The early emission, the secondary electrons are in red, and the primary electrons are in blue. And what we usually see is the blue. That is the, but if you have the modeling, if you have the data, if you have the spectra from early to late time in wideband, here ALMA is really critical, because we are talking about at least 100 gigahertz or more. So ALMA, updated ALMA, with 10 times higher sensitivity along with the VLA, ngVLA and SK will be very critical here. And then you can see the early time contribution, thank you. Early time contribution from secondary electrons, which will certainly decay faster, and then you will start to see the contribution from primary electrons, and one can infer the presence of hadronic kind of particle acceleration. And you can, if there are sensitive gamma ray telescope, one can see some gamma rays from these supernovae also, and neutrinos also if possible. So I'm going to summarize. Of course, this I've already said. So we need ALMA plus SK and ngVLA for this kind of science. And I want to summarize that we are really going to, of course, people have talked about, detecting a lot of transients, but here we are going to really classify different kind of supernovae. We are going to build the realistic model, and the plot I'm going to show you, the diagram I'm going to show you, this most important diagram of this talk, and that is from spherical models. We are going to build the realistic cow models, and for that it is important to do this kind of science. Thank you so much.
So do we have some questions for Poonam? Excellent.
Hi, Poonam, great talk. I'm really curious about the secondary electrons that you mentioned. Is there a particular kind of shock where this is expected to be more efficient?
So this simulation I talked about here, the simulation has been done, and it's shown that if the mass loss rate is at least of the order of 10 to the power minus 2, And then there is a possibility that you can create in just a very regular supernovae kind of scenario. You don't need any extra scenario, and you will be able to create these, inelastic proton-proton collisions. But of course, it's a simulation, we still don't know. But there has been some papers, by this group and the group from Japan, and they have shown that it's realistic model, and you should be able to see in few years.
Very cool. Thanks.
Thanks.
All right, I have one for you.
Yes.
So you mentioned using the long baselines to image the size scales for these things, right? Do you think it's possible to do supernova expansion parallaxes with ngVLA or SKA in ways that would be really relevant for improving our understanding of the Hubble constant?
I believe that question to the cosmologists. I don't know. Yeah, no, I think Hubble constant, I still really feel that gravitational waves method, which James told, I think that's one of the coolest way to, constrain our Hubble constant, but we need at least 50 or 100 neutron star mergers and good VLBI observations of those to do that. Supernovae are very close by and, not really that good.
All right, do we have any other questions? Okay, if not, let's thank Poonam again.
Yes.